So I want to just review, and you have this in your notes, but it may not make sense in terms of the stages. A charged particle being fired into a magnetic field will experience a force magnetic. So I'm showing an electron, and that's what you have there. All of the circles show the magnetic field. It shows like a region of a magnetic field that's all directed into the board. If you were to analyze this movement, so the electron's coming in, by the way, it's coming in perpendicular to the magnetic field. So magnetic field's in, electron like this. As soon as it enters, you would use your left hand, your third hand rule with your left hand. When the electron enters this region with the magnetic field like this, it will get pushed down. Okay, so there's our third hand rule application. And initially, if the field is strong enough, it will start to do this. Okay, so the electron will be pushed downwards. But what is really cool about moving charge is by the time you get to this point, now the electron is moving down. So you can kind of get the idea. Now, if you analyze its movement, your thumb is pointing down. Your fingers are still pointing into the board. So where's the electron going to go? Yeah, you see that? So now the force on the electron will be directed in. It'll be directed to the left now. So what's really cool is if the magnetic field is strong enough, and if the charge was moving at the right velocity, you can get circular motion, okay? And you could actually trap the electron in a sense. Like you could shoot it in here and it would just get stuck in a circle, okay? Now that doesn't always happen because if the electron's traveling really fast, it might do something like this, okay? It might like actually just kind of start to be pushed, but it's going so fast, it will exit the magnetic field and then leave at a new direction, okay? Or if it's really, really strong, maybe it'll have a really tight radius, okay? Because or if the magnetic force is strong enough and it's not going very fast, okay? But it does need to be moving, and that's what's emphasized in the drawing that you have right there. So this is not on your formula sheet, and I'd encourage you to add it because you can derive it from it, but it's not directly on there. The force magnetic, which is always directed towards a center point, that is causing centripetal force. Okay, so the force magnetic is causing centripetal force, and this is what we learned in physics 20. Okay, when an object is moving in a circle, there's a force, a center-seeking force that's acting on the mass. Okay. So the most common form that we expand these both into, obviously in this case, we are dealing with the other formula that we introduced a while back for the force magnetic. It's going to be QVB, okay? Q times the velocity of the charge times the strength of the magnetic field. The most common centripetal force formula, is mv squared over r. Okay. Now there is another variation, m4 pi squared r over t squared. I haven't seen that needed very much in physics 30, but it is a possibility. 99% of the time, this relationship will hold. T is the period. It's the time it takes for the, in this case it'd be the electron, how long it would take for the electron to go around once. Okay. So this one might pop up once in a while, but largely you're just going to deal with this. And what I want you to just see here, and some of you can maybe tell already, this velocity that the electron has coming in will be the tangential velocity of the electron as it goes around in a circle. So these two V's are the same, okay? And what happens here, you can see right away, if we had to say solve for R, which is a really common one, okay? This is using, it's what's called a mass spectrometer, actually. We'll talk about that later. You can shoot ions into a magnetic field and measure their radius. And what's really cool is you can work backwards and figure out their mass, which is awesome because it's really hard to find the mass of an ion. But we can do it this way using this math. The point is, though, is that these This V will cancel one of those, and you'll actually get a relationship that looks like this. Okay. Now you don't always do that because sometimes we're doing other things, but one of these V's will cancel out. You can divide both sides by V, and then we could solve for R if we had to. It would look like this. mv over cube v. If we needed to solve for the mass, it would be qbr over velocity. Anyway, I think you guys are fine manipulating the expression from here, but it's really versatile and useful. Okay, so the big takeaway, though, I emphasize it in bold in a number of spots on here, and right at the top I did, the magnetic field causes circular motion. Okay. Magnetic fields cause circular motion. And the separation we need to make here is a significant one because it comes up a lot in theory, and I tried to say it in different places on the front page. Electric fields don't cause circular motion. They cause what kind of motion? You guys see it? Parabolic. Okay? So electric fields cause motion that's exactly identical to a projectile. Okay, so you'll get this parabolic curve as an electron enters, say, two parallel plates that have just an electric field. But a magnetic field causes circular motion. And, oh, yes?
If you had a big enough electrical field, could it be possible for for a parabolic motion to be turned to circular motion?
No, because, see, an electric field, the force from an electric field is always going to be in one direction. Okay, like between, that's a good question. See, between two plates, like if the electron's here, the force on the electron will always be down. Okay, but what's different is look at the force in the magnetic field. Because the electron changes its direction, now the electron's going this way, the force on it changes to the center. The force is not always down on a charged object that's in a magnetic field. So that's what separates the two. Okay. Now, there'll be lots of applications where you can. In fact, we could actually just use this same one just to show you a quick example here. So I don't know if there's any space around there on the front. I'll show just one quick one here. If we have another magnetic field, and actually I want to do this one, I want it to come out of the board, okay? So I'm showing a magnetic field coming out of the board, and we're actually going to send an alpha particle this time, okay? I'm going to shoot an alpha particle, positively charged, into a magnetic field that's coming out of the page, okay? If, oh, no, sorry, I want it to be into the page still. I just had to check that. We're going to assume that the alpha particle has a certain velocity. And, we don't know what it is. And that's what we're going to find. But what we want, normally, if the magnetic field was the only force acting on it, then using our right hand this time, the charged particle would come in and you know what? I just overthought myself, honestly. These are supposed to be in, or coming out. Because, no, I'm right again. Holy cow, what's that over there?
If they go in, it will go up. If they come
yes.
out, it goes.
So, right hand, my fingers point into the page, my thumb points in the direction the alpha particle is moving. The force on this would be up, okay? So when this alpha particle gets in here, it's going to experience a force magnetic up, okay? We're going to assume that gravity is part of this scenario, okay? Often the effects of gravity are really negligible, so we ignore them. But well, no, it still has mass, right? So what we if just the force magnetic was acting on this, it would go up. If there was no force magnetic at all, then gravity would start to pull it down. Okay, the force of gravity would start to pull it down. However, if the alpha particle, and this is a classic question, if the alpha particle flies through the magnetic field undeflected, this is a key word. There's other words like this one. If it flies through undeflected, what does that tell you about the force magnetic and the force of gravity?
The magnetic force is equal to the force of gravity.
Okay, bingo. So, and watch for that in a number of questions, because what it just means is you can equate them to each other, because whatever the force magnetic was, it's being canceled by the force of gravity, and we can expand both of these. Okay, so the force magnetic would be QVB, and the force of gravity would be mg. Okay, now in this though, I need to give you a couple of things. We're going to say that the magnetic field here it's a really weak field, 4.9 times 10 to the negative 7 Teslas. Okay, that's how weak the magnetic field is. And that's actually the only piece of information I'd have to give you for this, because, and if I say determine, we're trying to determine the velocity. Okay. So we want to determine the velocity of the alpha particle. How fast would the alpha particle need to be moving so that it does fly through the field undeflected? It doesn't go up and it doesn't go down. So we know the mass of an alpha particle, and you can get that from my formula sheet. G is just 9.81 meters per second squared. The magnetic field was given to me, and the charge Q would be double the elementary charge. We've had to do that a fair bit, okay? So just to rearrange this, it looks like it would be like this, okay? I divide the left side by Q times B and have mg divided by that. And let me just throw this in here. I think that's the mass of an alpha particle. I've got to make sure. Is that number enough? It's 6.5. Okay, 10 to the negative 27 times 9.81 meters per second squared, divided by 3.2 times 10 to the negative 19 coulombs. Okay, that's double, that's 2 protons, right? 1.6 times 10 to the negative 19 doubled. And then this magnetic field I gave you was 4.9. Okay, Tesla. Now, just to show you here, I am fine with you just realizing that if you derive all of this, you're going to get meters per second in the end. Because to get the units here, again, you got coulombs and Teslas. Okay, you'd have to expand these, and I'm fine with you just to recognize that this is going to come out as meters per second. Okay, but it's a really small velocity. I think when we're done, 416 something. So yeah, probably. Well, I just gave you 2 digits, I guess. 0.42 meters per second. Okay. So that's nice, and that's not very fast. But as you can see, gravity is super weak on this anyway. So we don't want the force magnetic to be too big, because then it would go up. So we can keep that down by having a small velocity. Anyway, so that's just a quick example of applying this relationship right here. QVB equals mv squared over r. For sure, if you can tell that a charged object is moving in a circle, that's your relationship. That's your go-to. All right. So, something quick that's fun to talk about with this. The Earth has a magnetic field, and as you know, it's reversed. It acts like a bar magnet with the North Pole at the bottom and the South Pole at the top, or the South Pole at the geographic North Pole, right? But the polar regions have a much stronger magnetic field than the other parts of the Earth, because that's where the poles are. That's where the magnetic poles are. When charged particles, like protons, there's even alpha particles, protons, and electrons, but it's mostly protons, I think. They are discharged from the sun in like huge amounts. There's huge numbers of charged particles that are shot out from the sun all the time. And so if we have a proton or whatever, and it's flying from the sun, and it gets into our magnetic field, typically well, the magnetic field has enough complexity to it that it's really rare that a proton would just get caught in a perfect circle. Most of the time, if you can imagine this, if a charged particle comes flying in at a bit of an angle, okay, then what would happen is it would kind of turn into a corkscrew. There would be, they call it a helical path, okay, because it's like a helix. It's kind of like my DNA helix, if that makes sense, okay? It's like this twisting kind of corkscrew movement because it's not coming in perfectly at a perpendicular angle. It's coming at an oblique angle. And so what happens is these charged particles will like get caught in the magnetic field and they will spiral into our atmosphere. Oh, but this is where it gets cool. When these charged particles do that, they actually excite the oxygen and nitrogen atoms that are in our gas, in the gases in our atmosphere, and they cause electrons in those atoms to jump up and then fall back down. We're going to learn about that later when we were talking about electromagnetism. But that produces light. And it produces the phenomenon you guys can maybe guess. What do you know that happens sometimes in the northern sky at night? The northern lights. Okay. What those are, that's actually oxygen and nitrogen atoms. I got to double check if it's one or the other. I think one is more dominant. But it produces a green glow, like a green light. Yes?
A few hundred years ago or so, or maybe it was just 100 years ago.
Record this now too. So Faraday's law of induction involved Faraday's explanation for how current can be induced in a separate circuit. Okay? Basically, Faraday, we knew that electricity could act like a magnet. Okay? So electricity can cause magnetism. Okay? Ørsted figured that out with running a current through a wire. We've seen that happen, how a current in a wire can make it act like a magnet. What Faraday was really curious of is, can we go back the other way? Okay? So electricity can produce magnetism, but can magnetism produce electricity? Okay? So can I use a magnet in some way and cause current to flow in a wire? Because if you can do that, you can make electricity, okay? Which no one had done up to Faraday's day. So Faraday conducted a simple experiment, and I'll show you a video of it that's actually really good. But the drawing is there, so you don't need to necessarily draw this. He hooked up a power source, okay, to an iron ring, okay? And what I want you to realize about this iron ring is that the wire that he wrapped around it, it's not touching the ring. The wire is insulated wire, okay? So like the wire would come like this and he would wrap it around and around, one side of the ring, and then it would came back to this side. So this is a separate circuit, okay? And it's insulated from the iron ring. So it's not like the bare wire is touching the ring. Then he did the same thing on the other side with a separate circuit that wasn't attached to anything, okay? And all he put in here was like an ammeter, okay? Now yours kind of just shows what says a galvanometer. A galvanometer or an ammeter, they both measure current, okay? They're measuring current flow. And what he hoped was that when he closed the circuit here, that the current flowing through this loop would create a magnetic field, okay, which could hopefully induce like a current flow in the iron ring, which could then induce it's another magnetic field. So we have electricity producing magnetism, electricity producing magnetism, and then that magnetism causing electricity to flow in this detached separate circuit. Okay. So as you'll see in the video here, he closed the gap, and initially there was a spike, like the ammeter read a little bit of current, but then it went right back to zero while the current was running here. It just went back to zero, and he was like, oh man, I guess it's not really working. And then when he disconnected it though, he saw another spike over here, but then it went back to zero. And that had him kind of puzzled there at first because he was disappointed that it wasn't as obvious as he thought. And then he realized that the current, that the magnetic field that's generated by this current, it needs to be changing. Okay? If the magnetic field that's generated by this electricity here in this one, if it's changing, then current will flow in this wire. And I summarized it right there at the bottom. A changing magnetic field, you could underline that. That's the important part of Faraday's law of induction. A changing magnetic field is needed to induce current flow. Okay? So this means that a permanent magnet can cause current flow in a wire if the magnet moves through the wire or if the wire moves past the magnet. Okay? So as you'll see in the video here, there's a really simple way to do this. If you just have, if you have a loop of wire like this, and you bring a bar magnet like this, you bring a bar magnet right here, okay? If you can move that bar magnet through the loop of wire, okay, you're creating a changing magnetic field because you're moving the magnet, and that will cause current to flow in the wire, okay? So either you move the magnet through, or you could hold the magnet still and move the loop of wire, like physically move the loop of wire, one or the other. Something has to be moving, but that was the key. That was what he concluded with in terms of what needs to happen to generate electricity. And then, what happened immediately after that is Faraday invented the electric generator, which changed everything, because now we could make all the electricity we want. We don't have to use DC batteries and then hook them up to wires. We can generate electricity by moving a magnet past a loop of wire, and that just opened up the electrical revolution. The last bit of theory that you need to know is highlighted on that last page, and it became known as Lenz's law. Okay, so. As you see there in the reading, Lenz was looking at, solenoids. Okay, and actually these are vertical, so I'll maybe just kind of sketch what you have here. So he had just a solenoid like this, and he was like, so according to Faraday, if you take a bar magnet like this, and you drop that into a loop of wire. Like we could do it sideways as well. Like you could, like I was showing you here, you could have north and south like this, and you could move the magnet into the coil of wire. So Lenz was just curious. He was like, well, if we do that, yeah, Faraday confirmed that there is current that would be induced in the wire. Like the wire, there'd be current that would be found in the wire as the magnet moves through it because of this law of induction. But he was like, but what direction does it go? What direction will the current move? Will it go, clockwise or counterclockwise? Will it go left or right? And he first off, he was like, well, what we know about the second hand rule basically is if current flows in one direction, then there's an induced north pole up here, or if it's flowing this way, then there'd be an induced north pole here. So he's like, if we're inducing current in the wire, it's going to make its own magnetic field, right? So that's sort of the complexity here. Like we're moving a magnet through the wire. We're going to cause current to flow in the wire, but as soon as current flows in the wire, it starts acting like a magnet. So we're like trying to keep track of both of these. What he proposed first off was, okay, let's say there is current flowing in the wire. Let's say that the current is flowing. Let's see here on the top. Let's see. My drawing is I'm like circling in it out like this. So we'll say on the outside of the loop, we'll say it's flowing like this. Okay, that's on the outside, on our side of the loop. So doing that would mean, if you use your second hand rule, your fingers would wrap around the solenoid and your thumb would extend in the direction of a north pole, the induced north pole. So he says this is one possibility, but he recognized right away that there's a problem with this, and that is if you were to drop a magnet into a loop of wire and this is what happened, there would be a traction here. Like this magnet would get sucked in and it would actually like accelerate and be pulled into the loop of wire. And it doesn't, Yeah,
it would
we'd-
be really easy.
Yeah, it'd be super easy, and it would kind of violate the law of thermodynamics or law of energy, whereas like you could input a little energy and get out a whole bunch, and that's not how the universe works, right? That'd be like doing it sideways. Like if I start to move this in sideways, that there'd be a south pole here and a north pole here, and you just barely nudge it, and it would go shook, and it would just like get sucked in. Okay. Now, I'll show you quickly with an observation that the reverse happens, but he recognized that right away. He's like, this could not happen. Okay, what I just showed you can't happen. What actually happens is the current flows the other way. Okay, I know my drawing's really messy here. The current actually has to flow the other way so that there's an induced north pole to repel the permanent north pole of the magnet coming down. And it would actually physically slow down the magnet because there'd be repulsion here as the magnet goes through. And that would mean that the current would have to flow. Actually, then the current would be flowing like this. The current would flow like that in the solenoid. Okay, so really the principle of Lenz's law, and that's what these drawings try to show, is you can see in black it shows the magnet is blue and red, but the induced pole that presents itself at the top of the solenoid is the same polarity as the magnet coming in. Okay, if we flipped it, it would be south and south. But what it does mean is that if you drop a magnet into a loop of wire or into, say, a copper pipe, because a copper pipe, if you imagine, that's just like really, really tight coils that are eventually just they're so tight together it becomes a solid pipe. That you will see that a magnet would actually be slowed down. So I have a demonstration and a video that shows that.